Hi folks, this is Shefik. Welcome to my YouTube channel. In this video, we are going to focus on approximate nearest neighbor algorithm and also implement it from scratch in Python. But before we begin, please like the video and do not forget to subscribe to the channel to stay up to date with the latest videos. Also, your comments are more than welcome. Thank you for your all support in advance. Approximate nearest neighbor algorithm is the backbone of many vector databases and vector indexes. Nowadays, for example, Spotify Annoy is using this algorithm to index existing vector embeddings, and in that way you can even find the nearest vector of a given one among millions or billions in just milliseconds. And the idea behind the algorithm is very simple. It's depending on just high school math information. So we are going to implement this algorithm in Python programming language from scratch. As the first task, let's create random vector embeddings. That's why I'm going to import random module first. Thereafter, in this experiment, I'm going to have 1000 instances, and here I'm going to build a for loop for I in range from 0 to number of instances. Thereafter, in this experiment, we are going to use two-dimensional vector embeddings. Let's generate a vector embedding. But in reality, we are using multi-dimensional vectors. For example, if you adopt the facial recognition model, for example, FaceNet is generating 128-dimensional vector embeddings. But in this experiment, we are going to use just two-dimensional vector embeddings because in that way we will be able to visualize them. And its x-coordinate is going to be random.random. This is going to generate a float number between 0 and 1. Let's multiply it to 100. In that way, we are going to have a float number between 0 and 100. And if we round this, we are going to have much prettier values. And let's do this for its second dimension. Then I'm going to store this x and y pair into a list. Let's initialize the list named vectors, and here I'm going to append x and y. Alternatively, we can import numpy dependency. Here, instead of storing this as tuple, we can store it as numpy array. We generated 1000 different two-dimensional vectors in this vectors list. Let's visualize it. I'm going to import matplotlib to visualize this. Import matplotlib.pyplot as plt. Thereafter, here I'm going to build another for loop, and in each iteration I'm going to call matplotlib's scatter. Thereafter, here I'm going to pass the x and y coordinates. Vectors get its I index value. I'm going to get its 0 index value because this is returning its x coordinate value, and get its 1 index. This is going to return its y index. Thereafter, color is going to be black and marker is going to be x. And after the for loop, I'm going to call show command of the matplotlib. This is shown very small. If I create a figure before this for loop, figure is going to be matplotlib's figure, and figure size is going to be a tuple, and let's set it to 10 and 10. Now it's much better. We have 1000 different vector embeddings, and we suppose that those embeddings are pre-calculated. Here, each x value can be a representation of a song in Spotify, or can be an image indexed in the Google. It can be anything represented by vector embeddings. And in this experiment, we are using two-dimensional vector embeddings to visualize. But in reality, you will be able to use same approach for multi-dimensional vector embeddings. Now let's set a target vector, and we are going to look for the nearest vectors of that given vector. And let's set it here. For example, the target one is going to be 50 and 50. Let's show this here as well. After this for loop, I'm going to get the 0 index value of that given vector and 1 index value of that given vector, but let's mark it with red. As you can see, the target vector is here. The task in this experiment to find the nearest vectors of this given vector. From this graphic, you can easily say that these are the nearest ones. It's easy because we visualize it, but please notice that in real world we are using multi-dimensional vectors and it's impossible to visualize. So we have to do something different. In this point, pick two different vector points, and these random points are highlighted with red markers here and here. Thereafter, we are going to find the equidistant line from those given vectors, and we are going to find the equation of this line. This is line because given vectors are two-dimensional. If given vectors are three-dimensional, then this is not going to be a line. This is going to be two-dimensional hyperplane. It's going to be always a hyperplane. So let's say this as hyperplane instead of a line, and you can see the equation of it. We are going to store this equation into a decision tree, and thereafter we are going to classify all these given vectors with respect to this hyperplane. If a vector is on the left hand side of this given vector, we are going to put that vector on the left branch. If it's in right hand side, then we are going to put that vector in the right branch. And in the second stage, we have a decision node, and it's storing the equation, and we have vectors in the left and right branch. In the second stage, we are going to pick two random points again, find the equidistant hyperplane and group them again. In that way, we are going to do this recursively and find a giant decision tree. Let's implement this. To store the decision tree, I'm going to define a class and let's name it to node. Thereafter, let's set its initialization method, and I'm going to have hyperplane and also value. I'm going to store the equation of that hyperplane in this argument and store the list of vectors in the value, and let's set their default values as none, and thereafter set the incoming argument values to the classes variables. Similarly, classes value is going to be the incoming value. We are going to have also left and right hand branches. This is going to be none, and this is also going to be none. Now we need to implement two tasks. First one is going to be find equidistant hyperplane from given two vectors, and the second task is going to be find the given vector is on the left or right with respect to the given hyperplane. As I mentioned before, finding the equidistant hyperplane from given two vectors requires just high-score math. That's why I'm going to create a function here and name of it hyperplane equation. And as input arguments, this is going to get vector 1 and vector 2. You may remember types of vectors are numpy array. As the first task in this function, I'm going to find the normal vector, and this is going to equal to the difference of given vectors. Secondly, I'm going to find the midpoint. This is going to be easy. I'm going to find the addition of these vectors and find the division of 2. And finally, I'm going to find the constant term. This is going to be calculated as numpy dot dot. This is going to perform matrix multiplication, and I'm going to send normal vector and midpoint. Finally, this function can return normal vector and constant term. Let's test this written function hyperplane equation for existing vectors. You may remember that I have 1000 different vectors in my vectors list. Let's test this for first item of it and second item of. Meanwhile, let me write these vectors. This is the first vector and this is the second vector. I'm going to find the equidistant line from these given vectors. As you can see, this is returning a normal vector and also a constant term. This response can be represented as 0.99 times x plus hd minus 0.64 times y is equal to 17.03. This is the equation returning from hyperplane equation function. And for this task, to determine a given vector is on the left hand side or right hand side of a given hyperplane, I'm going to create another function, and its name is going to be check vector site. And I'm going to send normal vector, constant term, and a target vector as input arguments. Thereafter, I'm going to find the matrix multiplication of normal vector and given target vector. Thereafter, if the result is greater than the constant term, then this means this is going to be on the right hand side. If this value is less than the constant term, it's going to be left hand side. And if these are equal to each other, then this means given vector is on the hyperplane. But I'm going to discard that equal condition and classify it as left. Our subsidiary functions are ready. I'm going to create the main function. Let's name it build3, and we are going to send vectors as input. Thereafter, as I mentioned before, we need to find two random vectors from given vectors. Let's create a variable first points index, and I'm going to use random integer from 0 to length of vectors but -1. In that way we can find a valid point. Similarly, I'm going to do this for second point. But in theory, first number and second number may be same number. That's why let's assign their initial values to 0, and I'm going to do this random check in a for loop while first point index is equal to second point index. If they are different, then this while is going to be terminate. And after this while loop, I'm going to get this index for the first vector and vector's second point index for the second vector. Then I'm going to use this hyperplane equation function to find the equidistant hyperplane for these two vectors, and this is going to be the hyperplane. Once I find the hyperplane, I'm going to classify all given vectors as left or right. Classify given vectors are on left or right with respect to the hyperplane. That's why I'm going to create left nodes variable at its initial value is going to be empty list. Similarly, right nodes is going to be empty list initially. Thereafter, I'm going to build a for loop for vector in vectors, and now I'm going to decide this vector is on the left hand side or right hand side with respect to this hyperplane. That's why I'm going to use this check vector site function, and hyperplane's 0 index value was normal vector, you may remember, and the second one is going to be constant term. Instead of constant term, I'm going to send hyperplane's 1 index value and pass vector to this is going to return site information, and this is going to be left or right. If site is left, then I'm going to append this vector to left nodes, otherwise append this to right nodes. And after this for loop, I'm going to have left nodes and right nodes. That's why I'm going to create a current node variable. This is going to be node class, and as you may remember, node class is having hyperplane and value. Hyperplane is going to be the hyperplane and the value is going to be vectors. This build3 function is going to return the current node. But you may remember in node class we have additional left and right variables, so we are going to set them before returning. I want to perform this split approach until finding a fixed size of vectors. I mean, for example, if I find 5 different vectors, when I divide the all vectors, then I can terminate it. That's why I'm going to create a subset size. Let's set it to 5. You can configure this later. Here, if length of left nodes is greater than the subset size, then we should continue to split the given vectors. That's why I'm going to call this build3 function recursively and send left vectors instead of vectors. And this is going to return a node. That's why I'm going to set this to current nodes left branch. Otherwise, current node's left branch is going to be a node and value is going to be left node. But please notice that if I call build tree, it's returning a node with hyperplane, but in this case, it's not returning a hyperplane. Similarly, I'm going to do this for the right hand side. If right nodes is greater than subset tree, I'm going to set the right hand side from nodes coming from build tree, and here I'm going to send right nodes. Otherwise, right hand side is going to be a node with just right nodes. So in that way, build tree function is going to be recursive. I'm going to call this build tree function with my existing vectors, and I'm going to set this to 3. My tree is built very fast, and let's remember the vector we were looking for this. Here I'm going to build a for loop while trees value, this returning the all vectors for a layer. I'm going to find the length of this while this is greater than the subset size and trees hyperplane is not none. Then here I'm going to call the function determining the given vector is on the left hand side or right hand side. I'm going to call this, and vector is going to be the target vector v. Then normal vector is coming from trees hyperplanes 0 index value, and similarly constant term is going to come from trees hyperplanes 1 index value. Now this is going to return to left, so f side is left. I'm going to get the trees left hand side, and this is going to be my new tree. Otherwise, my tree is going to be right hand side of my tree. Here I want to print some blocks, go to left and go to right. And here I'm going to also mention the number of vectors, tree value length. I can use this. Similarly do this for the right hand side. As you can see, it can find results in 9 steps, and the nearest neighbors of the given vector v's can be found trees value. These are the vectors that located nearest to the given vector v. As you can see, in the first stage we have 1000 different vectors, and if we would apply KNN algorithm instead of ANN algorithm, we need to compare the given vector v to all these 1000 vectors. So its complexity would be O1000. On the other hand, we built a binary tree and store all existing vectors into this tree. In that way, we are able to find the nearest vectors of this given v in 9 different steps. In other words, instead of 1000, we find result in 9 different steps. This algorithm is 111 times faster than the KNN algorithm if the tree is built in advance. Finally, I want to visualize these nearest vectors in this illustration. Here I'm going to build a for loop for I in tree.value, and each one is a nearest vector. Here I'm going to plot another scatter, and this is going to plot I item, and let's mark them with blue. So as you can see, red one is the target vector and the blue ones are the nearest vectors. So really they are located very close to the given vector. This shows our approach is working fine. If you expand this example, this experiment into n-dimensional, multi-dimensional version, this approach is still going to work. So even though you will not have a visualized version, you will be able to find the nearest vectors with this algorithm. So in this video, we focused on approximate nearest neighbor algorithm instead of KNN algorithm, and implement it in Python programming language from scratch. If you do like this video, please do not forget to like it, and also please subscribe to this channel. Also, if you make comments to this video, it will help me to reach more people. Thank you for your all support in advance, and also thank you all for watching, and see you next time.